We are starting the afternoon session. It's a pleasure to have Ron Heiting, who's going to speak on the variations in the theme of Hitchin. Ron, what is it?
And then we can go back and then
No? Well, it's a pleasure to be here and participate in this celebration of Nigel's work. It's amazing how many different projects over the years I've worked on, each of which started by introducing the Hitchin system or doing something with the Hitchin system. So I thought I'd talk about some of the things that can respond.
Italian?
Yeah.
No, it doesn't.
No. So yeah, so the goal of the talk is to help celebrate Nigel's 50 years of contributions. And I'll try to do it by exploring several recent and ongoing research issues stemming from his famous integral system. Namely, I want to talk about connection with superconducting field theories of class S. I want to talk about a universal Hitchin system over the Deligne-Mumford multiplication. I want to discuss a little bit the geometry of the base. And just for fun, talk about connections with the Deligne-Simpson problem. Yeah. Is the mic not working?
It is.
It should be. Better now?
Yeah.
Thanks for letting me know. So, just what every talk here has already mentioned the Hitchin system, so I'm not going to spend too much time reminding you of what it is. But the basic input is we have a curve C, a reductive group G, and a principal G bundle of the C. If you prefer, you can always take G to be Gn, and then G is essentially a vector bundle. The Higgs bundle is a pair of phi or phi, which are really twisted in morphism. There are various versions, the static version, the equation, with conservative involved, never mind. Similarly, there's a simpler space design where you just break the phi. And what that is done is contain the X, and the static level is actually equal, and the JK level is within no one included. So Hitchin constructed this map from the Higgs moduli space to a base B. In the case of G of GLR, this base is there were to point, was it no later? Okay, well, anyway, so the base is going to be the sum of Fourier differential on that curve. And that given by trace of the power. With general G, you do essentially the same thing, where R is the rank of the group, and the R invariants, R basic invariants of the group, which agrees with what's called the PI, and you take the canonical bundle to the PI power exception, take sum, that's the two base. And the more interesting version is to take B to be global sections over the C of this somewhat strange quotient to take the canonical bundle to the line bundle, convert with the maximum non-zero plan. So now you have the vector bundle. And we actually divide root extends to that to take the quotient. If you work out this B is the same as the proof B, a point in base determines the camel cover, which is a W Galois cover of the curve C. Namely, it's just the image of C in P10 to KC without the double quotient. So you think of the little b as giving a map of the curve into this total physical quotient. The total physical quotient has a double cover, and you just put it back. Okay, so the key result are that Higgs is symplectic, and it contains the quadratic value of one with its natural symplectic structure. The Hitchin map H is proper in Lagrangian, and the fibers are maximum isotropic, and the general fiber is generalized primitive spectrum, which means that in given situations it can be the Jacobian of the square curve or the frame of it. I prefer to work just with camel coverage. People are more used to square curves. Those are obtained from the camel cover by single representation by the basic quotient of the camel cover. Okay, so this is work of Hitchin and many followers, and it could be some Kazdan, Falking. It's a work of myself, even without guys going. The version that I will mostly use will be the normal version, case of closed function. So we fix the reduced divisor, effective divisor D on the curve. And basically we try to allow pole that one D, first order pole. So we replace the canonical bundle by differential of those first order pole C and points B. We have Higgs sub D, which parameterizes the Higgs bundle with first order poles at point D. In other words, the formula there, and just replace the canonical bundle by D2. There's an analogous which obeys B sub D, which is the sum, again, I going from 1 to the rank, global section, and then just replace K by K of D. And then the Hitchin map between these three. So far, it's not really boring, but let O be a collection of quadrant orbits and insert that at PI. So for each PI, we choose a conjugate cloud. Enter the quadrant orbit into the algebra at that point. So script O is a bunch of conjugate clouds that talks about. And then within Higgs sub D, we have Higgs sub O, which is the subset where you impose the condition that the residue for PI is in the conjugate class. So this started by the work of Mossman and Donagi. One new feature of the Higgs sub D is no longer symplectic and so on. In fact, the Higgs sub O, the one that is described above, are symplectic the restriction of the normalization map HD to one of this subset is the Lagrangian with image feasible. In other words, you have a Boltzmann system, you have a foliation by symplectic leaves. You have one big map which when you restrict each symplectic leaf becomes a network system. So one current interest in these things comes from the superconformal field theories of class S. These start with the six-dimensional theory, which depends on very little. It depends only on the algebra, reductive G. But then you can packify from 6 dimensions to 4 dimensions on a 2-dimensional real thing, which surface of curve. So you choose additional input of the curve C and a bunch of points to D. And the residue of the points are confined to nipple and orbit. So this is something that as mathematicians might seem a little strange. Why do you restrict to nipple and orbit? The best answer I got from physics friend is that you should think of the eigenvalue of the residue as mass deformation. And since you want the superconformity of theory, it has to remain massive, so that's a main point. Mathematically, it's not a very serious constraint, so much for that say would apply to non-important case as well. Anyway, this 4D quantification and the Coulomb branch, which just happens to be the Hitchin base. And if you combine it by further to a three-dimensional theory, then the effect of complex line of the circle is to add into the real varieties to the five, which is how
Is it possible to say in 30 seconds what you mean when you say backslide from 6D to 4D?
no.
Take it more time.
Well, it just means that there is a consistent procedure constructing a four-dimensional theory, which is the superconformal theory in four
Is
dimensions.
this the thing where you take a six-dimensional thing, you assume that two of the dimensions are really small and wrap around, and so the result.
Yeah.
Essentially.
And then you perform some magic and you come up with a theory in four dimensions. These things also have X branches, those will make frequently like later on. So in the case of SLN or GLN, the Newton conjugates classify index by partition of the number n, which we always write in standard descending order. So P1, P2, P2, and so on. So if you have a partition, that determines a bunch to that box, and you take a regular important in each of those blocks. So let's see. The generic regular element does not correspond to it. It is not important. So this doesn't enjoy that you can use to describe all the partitions, of course. But in this particular description, the regular, the generic regular element does not occur. The regular is important corresponds to the partition, and the subregular means you move one ring over to the next place and so on, until the smallest nipple, which is 0, corresponds to 1, 1, 1. We have 35. This would be the regular representation. This would be the subregular. This would be the 0. So I want to introduce two numbers, pi and pi. You can think of these as meromorphic sections of the canonical bundle, or as sections of the twisted canonical bundle, which will have some branching power. So let pi be the order of the pole, and chi be the order of the branching. Of course, pi plus chi is just j. So the subscript I refers to which point we're at, and the subscript j means the invariant name. So you're taking voice when you're just taking the j. Okay. So one amazing thing about this basic case type A, the SLN case, is that you can compute these things and they give you complete information. So here's what you do. You have some partition. Something like that. You write the integers from 1 to n in it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 6. the ones without the doing SLN, we just skip that. We look at the row numbers. These give us the column. So the pi's are given by the complementary number. So it would be 1, 2, 2, 3, 4, 4, 5, 5. In other words, you can get the orders of the poles just by listing them, listing the numbers in the corresponding Young diagram, and you stutter every time you start a new row. So you see that for the regular case, that's all the Kaiser 0, and so yeah, the Kaiser 0 and the Kaiser J pretty much by definition. In the regular uniform case, each of these comes down by 1. So the order vanishing is 1, so the pole is J minus 1, and so on. So there's the special feature of this case, which is that the visible, the image of the locus of the coordinate orbit, the linear subspace of the full BD. The equation expressing it are simply this chi, the fact that various the residue of various powers of phi have to vanish this annoying, either linear condition or coefficient. This is not going to be true for the angle. And in particular, the orbit always uniquely determined by knowing these integers chi. And here's one way to see it. Given the pi, we get line bundle LJ. This is not the J power of the line bundle L. This is the J letter. So it's Kc to the power J, twisted by Pi, is not twisted pi J, or pi J level. So this is a line bundle of some particular degree, which are according to J. If you want to do the story for other groups, there are all kinds of things that change. So, first of all, there are two types of partition that you should consider: the Hitchin partition and the null partition. In the case of SLN, you just dual partition. In other words, instead of looking at a bunch of rows, you put the same length on columns and read it the other way. It's just a transport in diagram. So in type A, these things correspond to each other by transposition. And that's for the other types. There's a huge body of work on that, starting by Stockenstein, by Carter, Kajan-Lustig, Kraft-Puchesi, and so on. There's a map from the noun coefficient to the Hitchin coefficient, but it's neither injected nor subjective.
Can you say what is the noun partition and the Hitchin partition? I didn't catch that.
Yeah. So I'm going to be a little vague with that at the time. In the case of SLN, the Hitchin partition gives you the size of the digital blocks, while the noun partition gives you the dimensions of the cyclic module. So it's just the transport. Yeah, for other groups, there's a way of there's a bijection between the noun partition and the orbits. And then they apply it to one to the Hitchin partition. So a special partition is one that isn't the image. And for special partitions, you do get a rejection, but they're only from a subset of all partition. So for example, in type N or XO to N, so you partition the partition of the number 2n, with some condition on it. And it turns out that it's special if there's an even number of odd parts between any two even parts, or in the beginning, before the person. So it's pretty captivating set of conditions that it just end up to be the right one. Okay. The physics literature has that famous dichotomy of good, bad, and ugly theory. The definitions are funny but confusing, and there doesn't seem to be a great unity between the authors. So we decided we just had to abandon them, and we're going to work with a dichotomy between bad and okay. So okay means either good or ugly. Yeah. So okay is not bad. So yeah, so I think everybody can with it and understand. We give a reference to the movie. So now we gave a reference to the gunfight. Okay. Gunfight is over the 4 hours. Anyway, a theory is ugly, or and then people say it has multiplied. If the last DI in sequence of degrees, so remember I gave you formulas for the DI, those are the degrees of the line bundles for sections that terminate to base. If the last one happens to equal to 1, the reason this is interesting is because cat is middle convolution, which is somewhat mysterious procedure, replacing an ugly theory of rank R by another of rank R minus 1, which makes the value now. That has the same degree DI as the trailing one deleted. So the effect of that on physical branches is the Higgs branch shrinks. We talk about removing a hypermoduli. The Coulomb branch is unchanged. So from the point of view of just the Hitchin system, we don't see any effect. You could say that performing this middle convolution does not change the model. Geometrically, I believe what's happening, and I haven't written that down carefully, is that an ugly theory is one in which the generic spectral curve is singular. In fact, you want to have a base component. So it's like the picture for isotone minus 1. You have something symmetric plus the 0 section. You can imagine that once you start imposing dimensional conditions, you'll have more and more possibilities of that. And then the convolution simply reduces by 1 the multiplicity of the fixed component. So it gives you a new system with simple curves. Anyway, I'm doing that. So to understand superconformal field theory on a degenerate curve, which is something that physicists want to do, because you can hope to do things like reversing the formula, something that we come up with some quantity that the information is there, and then you generate all the way to the model of the generate quantum boundary computed there. So we need to extend the Hitchin system to stable curves, or better, to get a flat family of Hitchin systems over the entire Deligne-Mumford multiplication. And let me just point out, since people were talking not the first couple of days about studying the asymptotics of the Hitchin system near a single curve, that's different. They were talking about a smooth base curve, a single spiral curve. I'm talking about a situation where the base curve itself becomes single, and of course all its covers. So in type A, we have the naive Hitchin base. So that's called B prime sub O, which is just direct sound global sections of the line length Lj that we had. So the formula for Lj was canonical balance of the J, twisted by combination of the points, was not listed, the pi J, which I showed you how to compute. The problem is for singular C, the rank of this B prime O can jump. So we can put these straight L's into a line belt curly L line on the universal curve over Deligne-Mumford. But our parallel side does not vanish. That's the answer. It's intuitive that the family is not flat. So in the work with balance over minor and Whistler, we show that we can modify L prime to L. So Lj is defined to be sections of L prime J, which vanish in various things. So remember, the script L is bundled on the Deligne-Mumford multiplication. So I'm saying, look at any partition of D into two complementary sets S and S prime, and assume that each of them has at least two points in it. So the first case to occur is when D is 4 points, you break it into two and two. So script C sub S is the boundary divisor of moduli, parameterizing those reducible curves. Say we can do it in CS in CS prime, such as the puncture PI lives in CS. If I and S, it lives in CS prime, if I is in S prime. In other words, the partition of D into two disjoint types determines a boundary dividing moduli. The modification we make is we subtract a linear combination of those boundary components. So this is summation of all S's. And the multiplicity that we subtract is number NSJ, which is given by a somewhat complicated formula. It is what it is. The way to derive it is that when one of the two halves happens to be smooth, which is the generic case, then this number NJS is just the first cohomology of the line J restricted to that component. That is basically the authentic thing, the thing that makes it be non-flat. So you just reduce the degree by that, and now you have something that will give you a flat boundary of the category. In that lots of generality, we can ignore nodes that are not separating. They don't contribute. And you also need the genus of the curve in question, or the component in question to be zero. Otherwise, it's H1 of that. So our theorem is that the modified Hitchin basis form a vector bundle over MJ and bar. It's the direct sum of pieces given by the J's. And the J's piece is the direct image of both L, J, and L prime J. So even though there is an L1, you can take the R0 part of the star and calculate the correct answer. But it's different than the cohomology of that part. It's the same about base chain. Or suddenly, as a big joke with students. Okay. So as I mentioned, the first non-trivial case is N04, where the moduli space is P1. Let's do the simplest thing we can, which is put 4 regular nilpotents. In other words, take all those vanishing characters in one with a total of points. So the Hitchin base can then be identified. Well, it's just a vector bundle of P1, and we can write it some of that and work out what it is, depending on whether J is even or odd, to slightly different formulas. In particular, this gives a filtration of the Hitchin base that is invisible if you look just at one Hitchin system. It is only visible when we look globally over the entire modular space. And there should be similar structures in more complicated modular space, but they are not working that. Okay, so next we want the proper version of this modulated class. So we've gone halfway towards constructing a universal Hitchin system. We compactified the family of basic. Now we need to compactify the postgame. So there was some work on that by Balaji, Barik, and Nagaraj some years ago. There's a recent paper by Ben Batsat, Das, and Pante. And I'm working with Andres Herrera, hopefully it will appear sooner than the paper was cards. So BBN considered the case of a single node extension, which is a great start, but you need to set up a combinatorial game to allow for further similarity. BDP treated the unpunctured case. So there are no puncture, BO is with B. There's no personal structure, it's just a symplectic structure. They also work with respect to DVR and they're able to completely treat that case. And the paper that the group finishing was still in type A, but we focus on the punctured case because that's what we need to look for filters. And related to the modified Hitchin base. And we also get a global relative personal structure. So the idea for Tony's paper and ours is the same. You look at the G-Higgs model, physical stable. So that's the again for instead of a it's going to occur like this. You resolve that by taking one of the singularities and replacing it by a tree. So have all occur. Here you can put in one or more trees if you want. And you have to come up with the right definition of what it means to have a stable Higgs bundle over one of these pre-stable curves. What happened?
You made that back because we had.
So this is the G-Higgs bundle. Let me not get into too much. Here are the results. So there exists a modular space H of normal Higgs bundles or punctured Higgs bundles over a moving stable punctured curve. Only there's a relative log Poisson structure relative to the map to MG in bar. A modular space HO of normorphic Higgs bundle with residue in specified Newtonian convex classes. Again, over the movement curve. And on it, there's a relatively long symplectic structure, again, over MG bar. And finally, there's a proper flat log Lagrangian Hitchin map from HO to BO.
So is there a non-trivial log structure on the moduli space over the boundary?
Yeah.
It's like a semi-stable degeneration.
Right. Yeah, so the picture of the very this universal object. There are really two of them. There's the unconstrained one and the one where you constrain to lines in the middle of it. The unconstrained one gives you a Poisson or log Poisson system. The constrained one has a Hitchin out. It doesn't go to the naive Hitchin base, it goes to this modified Hitchin base, which will point out gives a vector bundle. And over the interior, of course, it restricts to the initial object. Presumably, you can replace the conjugacy classes by arbitrary ones. In other words, to include mass information, we sort of have the argument that haven't taken it down yet. What's completely open is to work on the generals of the Hitchin base and the system for other groups. So if you do look at these other groups, there are numerous phenomena we can avoid them. I'm going to do a decent job explaining them. Let me just give two examples of interesting issues. Okay? So question, is the base smooth? Well, for type A, it certainly is. But it's in the next phase. What about other groups? So my collaborator this student Chakatana wrote a bunch of papers where they showed the answer is yes. While Borrell and Cameron Couture have paper where they showed the answer is no. So obviously they are answering slightly different questions. The BK base is by definition containing B and D. It is given there by fundamental constraint on the component. In the case of type A, those constraints are linear. For other cases, they are quadratic and pi. So the image is just some variety of that unconstrained base. And it turns out that in many cases, that's a record singular. On the other hand, C and D have a different version of this constrained Hitchin system where the CD base is always a vector space. Their base maps to the decay base. Simply. So usually this map is birational. So you're just mapping a vector space to something that crosses itself, or it's cuts to or something like that. But there are other cases where it was actually applied to one. So in a recent paper, we analyzed that for type D. In particular, there's some distinction between odd and even constraint. We described two important features which distinguish type D from type A. The first feature, which we term even type constraint, arises if an partition labeling the nilpotence has even parts. In this case, our Hitchin image is non-singular, and that's different from the one studied by B&K. We argue that our Hitchin image always globalizes. So this was talking the local, that you're working not with a curve, but with a neighborhood of a point of the curve. And then there's a question of whether things globalize or not. So these are always do globalize on the curve. So in other words, the base of an integrable system. The second feature, which we term odd type constraint, is related to a particular finite group, which is a modification by Achar and Somers of something called Lustig's canonical quotient. So the issue is whether that group is trivial or non-trivial. It's always a finite group, and the parameter is the choices for the local Hitchin base. So additionally, we also show that the finite group encodes the size of the dual specialty. That means there was this map from now data to Hitchin data, which we said has an image of the special classes, and then what's the fiber. So the size of the fiber is the size of each group. You don't have a connection there between the two, and that's really understanding. And here's something that I find very intriguing. And again, I don't understand computing. So let X and G be anti-symmetric matrices, where X is important, G is vector. So we deform X in the direction of G. In other words, we look at X to PG with the graph. It's a small graph. Then we take its coefficient of polynomial. In other words, the determinant of X to G minus plus lambda identity. You expand it in terms of the two variables, lambda and t. So we're expanding first in terms of lambda, starts with degree 2n, and has various low degree, all of which are even because it's Swiss. We write the coefficient of lambda to the twice n minus k as a leading term, which is c to k times the power of t, plus higher order term, which you can go. And the thing that I'm calling chi here, combinatorially, here's how you determine it. If you take the sum of the pi, and then go to decreasing order. And if you have 2k, which is between the sum of the first with j minus 1 and the first j, then you say that chi equals j. You can go back and check that these chi's are exactly the same as the chi's that I have over here, because of the order of vanishing, determined by the yeah, but in the case of type T. So these linear coefficients C to K are polynomials on the algebra. Polynomial degree to K. That's how universal polynomial. Just say whatever. So we worked out a lot of cases, and well, I already told you what it means for partition type D to be special. So the conjecture is if P is a special partition in the sense, in the sequence of parts has a jump. So P to I plus 1 is actually less than P to I rather than the then take the sum of the, so the P's here are the parts of partition and not the points. I just realized that using P for two different things. Anyway, take the sum of the parts up to 2i, call that twice ki. And then the claims of this polynomial happens to be a perfect square. It's a polynomial function under the algebra. Just like the determinant. The determinant is the extreme case. The determinant is the square of the problem. So the prediction is that there's a whole slew of other problem-like features that I wouldn't think of. And they come out of these into the systems. Any question?
Can you say again this what special is for SO2A? You can say there.
Yeah.
You just say it.
So, especially in general, says that this class is the image of the spot point now. In this particular case, it says that the other prediction that has a bunch of parts in the same order. Look at the even ones and the odd ones. Even if the number is even, like its position. And then count between any two even ones, or to the left of the biggest even one, how many odd ones there are. And that number needs to be even. Pretty strange condition. Okay, so good. So let me talk about the possible application to and Sheffield and connected it all. That Carlos many years ago pointed out a connection to the Deligne-Simpson problem and Hitchin system. Given the collection of conjugates of classes in geometry, we want to try to find representatives whose product is one. Equivalently, we're looking at the character variety of representation whose given conjugates classes in one or form. And the question is the character variety empty or not? So you can think of it as working on the rational curve C and just one marked points we have multiple residue assigned to them. And Carlos needs to make a technical assumption, which is that at least one of those should be regular semi-simple. So we expect that to be the last one if I'm calling number one. That one and then everything. So the additional character variety is not empty, yes and only yes. It's numbered, well, two numerical conditions. Let's not get into that, the complicated. You can just see what the conditions are. So his idea is a set of a combinatorial game involving the permutations of the parts of the Hitchin partitions. The stable solutions give stable bundles with the desired residues. It shows that the game has a stable solution under the hypotheses. And using Hitchin system and the Hodge theory, it produces the desired local system. So, where you play the game, you have and well, let's say, so looking at an array, where each row corresponds to one of the functions. And each row is partition according to partition of that 11 rows. So you just write the partition as a bunch of blocks. And then you get to move the blocks around within each row. What you do is you take and cut it and do what you want. You can see how many times you within a block, and how many times go outside the block. Count them, count two in the block. So that's Q, I, and one. Is the number of connections between column I and column I and one. In this picture. And then you find slopes. So mu I and MS1 is going to be Q I and MS2 and minus 2. The two of us comes from the canonical. Pure itself is used to zero than that. And then define slopes. So you start with your slope, and then you get various slopes, depending on the pattern that you're looking at. And such a permutation is called stable if it's strictly below the second line at the beginning of the game. So this is an example of a winning solution, a stable solution.
Good luck. Okay.
Which is what we did, didn't it? So the conjecture that I want to discuss, it's okay in the sense of the different form of field theory. And that means the basic relation just says that all the di are bigger than minus one. Those are the degrees of the Hitchin line. Now yes, some permutation gives a stable solution. So in general, both the OK condition and the existence of a stable solution are stronger than the Hitchin condition. In the regular semi-simple case, Simpson proves that these conditions are equivalent to the existence of a stable solution. And we can show that the OK condition is also equivalent to that. In general, Simpson's condition is too weak, but it seems quite plausible that the OK condition is exactly equivalent to the Hitchin solution. Yeah, the number of so yeah, the Q is the number of connections between the columns. I want this one I. The users I gave them. Stable solution is when the graph of slopes in y stays strictly below its second line. The i's are just the slope minus 2. When partitions are in the standard decreasing order. The OK condition is all the i's are equal to minus 1. Or proving here that the slopes are bigger than 1. Bring it to 1. So if you do the counterpositive of our conjecture, it says that some di is less than equal to minus 2. This is the statement about the standard decreasing order partition. If and only if there is no reorder which is stable. So evidence is there's one theorem that says in the regular Simpson case, since its conditions are equivalent to the OK condition, with lambda and J. And another theorem, written in smaller form, that's exciting, is that if some di is less than minus 2, then the standard order is unstable. Like the conjecture is that if so, di is less than minus 2, then all orders, okay, or at least one case, that's into whole.